an example to see if I can get it with image matrix, and I'm not able to show it.
Well, why don't you show me the example?
Okay.
Okay, questions?
Yeah.
Question, please. Okay, so let me start with an example today, kind of illustrate some of the stuff we've been talking about. I'm going to use this. Actually, I want to take a closer look at this example later. So that will be the real cube root of 2. So it's a root. It is real root of polynomial, but omega. That is to say, you can this cube's the 1, no smaller power of this is 1. Then these 3 fields are all isomorphic. All for the work that we've done, because all of these are Q adjoined with a root of x cubed minus 2. These are actually the 3 cube roots of 2 in the complex numbers. And so from field theory point of view, just purely considering this, these are all isomorphic to QX modulo this irreducible polynomial. This one is 2 Eisenstein with a field of rational numbers. And so these fields are all isomorphic, even though this one's real, these 2 are not real. And if you take the intersection of all these 3 fields, you get the rational numbers. Okay, so here we have (11). A be a field. And f of x, I guess I should say non-zero polynomial in Kx. We'll say that degree of f equals n. Then there's a simple extension field, okay, which is the following holds. Such that one, there exists an f such that 0. So in other words, there's a root of this polynomial in the simple extension field. Number two, the degree of F over K is no more than N. And equality holds but only if anybody want to take a stab at this? Mhm. And say, absolutely, that's and number three, if F is irreducible, in KX, then this field is unique in a certain sense. What I mean by that, it's unique up to a junction, unique up to K isomorphism. What I mean is an isomorphism of fields that fixes K. K of U is called the field obtained by joining a root of that to K. Okay, so why is this true? Well, so we'll start off. Factor. So factor this, origin you on KX. And lucky us, there's only one way to do this, really up to units, because KX is a unique factorization domain. I want this to be a prime factorization. So these are all irreducible polynomials. So just factor until you get irreducible polynomials. And of course, irreducible, I want the degree to be at least one. Degree zero polynomials sort of don't count. They're just constants. And consider, pick one of these. I'll pick the first one. Choice is arbitrary. There I go, throwing that word field around pretty loosely. How do I know that's a field? Oh, that's right, because P1X is irreducible, which means it's prime, which means in a principal ideal domain, it means it's max, right? So this is field. So this is indeed a field, and it contains K. So certainly you can put K inside there just by taking the element K from K and going with this coset. This is clearly 1 to 1. So K is a subfield. Now, what we want to do is I claim that U was a root of f of x, right? Or we can find a root in this field, right? Now, this is a field containing K, and I claim that my polynomial f actually has a root in here. Well, let's find this root. First, find a root of P1. And to this end, so let's consider projection pi so let's just look at the projection, take any polynomial to its appropriate coset. So pi g of x equals g of x plus the ideal now. Let me point out here that the way this homomorphism works is now note that if you look at pi of P1 of x, and notice that of course P1 is in this ideal, so this is 0 coset. So in other words, x, the image of x in kx mod 1 of x is a root of P1x. Right? So just take that homomorphism and see where x goes. It goes to pi of x, technically. That is actually a root of the polynomial P1x. And so that kind of takes care of it for us because the field kx modulo P1x has pi x as a root of so there we go. So U is the role of U is now played by pi 1x, right? It's a root of P of x, and since P1x divides f of x, then pi x is a common root. Root of f of x. I'll probably more common start calling this extension field F because I'm separating that every time. Okay. Any questions? Let's see. This degree is less than or equal to n. Okay. Let's look at the statement here. notice that the degree of F over K notice that this is the degree of one of X, you've seen that. And I don't know much, but I know that this is less than or equal to degree of F of X, which is n. And this other statement is, I think, pretty clear, because if you have equality, then degree of P1X equals degree of F of X. And so this implies F of X is irreducible. Right, because these have the same degree, they can only vary by a constant, so since this one was irreducible, this one has to be irreducible. Right, and on the other hand, if F of X is irreducible, then F of X must equal P1 of X. And so we get equality, right? Okay, any questions? Oh, yeah. This one right here, see if you can check this one yourself. This one, it follows actually from the last theorem that we had last time as well. Okay. Any questions? Okay, so let me give you this neat theorem, which is really pretty easy to prove. So I think sometimes it's easy to think that when you have a theorem that's not too difficult to prove, it seems like it might be a useless theorem. This is not true at all. And we'll put this to a good application here in just a moment. Theorem 8112. Suppose that we have K inside of F far fields. Such that the degree of F over K is n. It's finite. Then F is finitely generated ring. Actually, to say something that's finitely generated as a ring is much is a weaker statement than say it's finitely generated as module. So this one will be pretty obvious actually, because this is actually a stronger statement and algebraic. That's the more interesting part. Well, the finitely generated part is pretty easy because F is finitely generated over K as a vector space. Right. In fact, what this notation here means is that F is an n-dimensional vector space over the field K. So let, I don't know, U1, U2, UN be a basis for F over K, then F is equal to K, U1, U2, UN. This is you can see the difference in strength here, right? Because really what this is this is all rational functions in K and in variables, right? You've got all kinds of crazy crap in here, like U1 squared and U1 times U2 times UN to the 45th and U1 over U2, et cetera, et cetera. Certainly you can represent everything in that way because actually everything in F is a K-linear combination of just the first power of all these, right? So saying that it's a vector space, much stronger statement, right? So that was the easy peasy lemon squeezy part. This is the more interesting part, algebraic. But it's not too hard to prove either. So
Yeah.
let U be any element, yes.
You can prove that every element is algebraic of a base, and we are done, right?
Yeah, that's the strategy. So let U be any element in F you want. Note, the set 1 U squared U to the n is linearly dependent over K. Right, because actually I have n plus 1 things here. So there exists K0 up to Kn and K, not all zero, such that K0 plus K1U plus Kn UN is equal to 0. And since these are not all zero, that gives you a non-zero polynomial relation on U. So U is algebraic over K. Right? Questions? All right, so this gives us this is like a bootstrap theorem to give us this very important theorem about algebraic extensions. So if F is algebraic over E and E is algebraic over K, then F is algebraic over K. So this is transitivity of algebraic. If you have E over K is algebraic and then F is algebraic over E, then you're good to go. Okay, so how do we prove this? Well, let's let U be some element of F. And somehow I'm going to show that it's algebraic over K, right? Now I don't know much, but I know that it's algebraic over E. If F is algebraic over E, then I've got a polynomial relationship. En UN, En minus 1, UN minus 1, plus E1U plus E0, 0, with EI and E and EN 0, at least that one is not 0. So how do we make the jump? Right, so there's my equation there, and it tells me that that this U, this element of F, is actually algebraic over E. How do we jump to K?
Each EI is algebraic.
What's that?
Each EI is algebraic, so we would use that.
Okay, okay. And how are we going to use it?
We find a polynomial for each one, then we probably can plug it somehow.
Yeah, we could do that, but I anticipate a mess. Right. I look at the equation and it's speaking to me. It's those voices again. And what is this equation telling me? This equation actually says, let me give it a name. I'll call it star. Star is telling me more. Actually, U is algebraic. It's certainly algebraic over E, but you can do better. And this is actually the little stair step that we need here. So, everybody agree with this statement here, that U is actually algebraic over the smaller field, because really all we need are the EIs that are coefficients. So consider the following power. So consider this tower of fields. Let me point out that, what can I say about the degree here? Well, I know it's finite, right? Because E naught is an algebraic. So now we're using the algebraic stuff. E naught has some polynomial. I don't know what it is, but it's got a minimal polynomial. And the degree here is M1, say. Actually, let me call it M0 so I can keep track better. This how do you get this field? You get this field by joining E1 to here, right? And E1 actually has finite degree over K, so it's got that degree or less over K E naught, right? You have more possible coefficients here, so the degree could be smaller. So this jump is M1, and so forth and so on. Yeah, that's a terrible choice. Let's go M0. Let's call it something M1. Call this M spin. So in particular, the degree is equal to three. So so K, well,
No.
and now Right, and so now, look at the degree of
We're gonna join you.
K E naught E N U over K E naught E N. We'll call this degree, I don't know, little k. This is finite too, because remember, U is algebraic over this, right? And so the field, the degree K E naught E N U over K is equal to M0 up to Mn times K, which is less than infinity. Right? So K E naught E N U is algebraic over K. So U is algebraic over K. But U and F was arbitrary, so any element of F is algebraic over K. This is kind of an important idea using the field extension. Notice nobody wants to write these polynomials, right? In fact, your first instinct about writing those, they've all got some kind of polynomial, but that's really kind of clunky. Using this theorem about degrees of field extensions, we can get the algebraic without having to actually write down the polynomial, which is a good, powerful tool. Let me point out something. A couple of things about the theorems we've done. The first one is algebraics gets such a bad name, right? Because I is called an imaginary number, right? I hate that terminology. It's terrible. Of course, I is. I know what polynomials over Q are. I know what that polynomial is. And there, just like that, I build I. The image of X in that isomorphism is the element I. It squares to -1. Build that ring and you build something that squares to -1. Take the field of 5 elements and square 2 and you get 4, which is -1. I believe in I. When you start talking about pi and E and that's when it gets a little flaky a little bit, right? I'm sure some of those super finite people don't believe in, well, any of this. But let me point out something else. And this is part of the bedrock of ideas in this proof here. This field is algebraic over Q. And basically it's because any finite adjunction is, right? So if you have any element of this field, you can put it in some field. So if you take an arbitrary element out of it, call it E, then it sits and you can use the same techniques to show that this is an algebraic extension. And so therefore, every element in this is algebraic, and this is a very big algebraic extension. So the upshot is you don't really need it to be finite dimensional vector space to be algebraic. If it is a finite dimensional vector space, then for sure it is, but there can be even bigger algebraic extensions. Here's another groovy consequence that, and this is one I've been teasing you all about for a while. So here's a corollary. Let alpha and beta be algebraic over K. The following are also algebraic. Number one, alpha plus or minus beta. Two, alpha beta. Three, alpha over beta, if beta is not zero. So, let me, actually, write that up. I'm gonna write them upstairs. Now, I promised you all this earlier, sums, products, quotients of algebraic elements are still algebraic. Now, again, alpha has some minimum polynomial over K, say P of X. Beta has some minimum polynomial over K, say Q of X. Good freaking luck finding the minimal polynomial of alpha plus beta, alpha times beta, alpha over beta. So, as I pointed out, when I was kind of beefing up for this, that we needed to consider something else. So consider I like this proof because it illustrates how easy things can be if you think about it the right way, as compared to it's impossible really to find them. Not impossible, but it is a Herculean task to find a polynomial for sums. Look at this extension right here. This is finite. Because alpha is an algebraic element, and whatever the degree of alpha's polynomial, it determines. So one of you asked, could you ask about the degree? Suppose the minimum polynomial has a degree n. This is finite as well. And this is a little bit flakier. Notice beta has a minimum polynomial over K, say of degree m, right? But I don't really need a polynomial. Well, I might not need a polynomial that big because actually I just need to find the polynomial of beta over this field, which might be smaller, right? So the degree of this extension is finite. And so if alpha's polynomial has degree n and beta's polynomial has degree m, then what I can conclude is that field extension is of degree n, m, or less, right? So in particular, K alpha beta is algebraic over K because it's finite extension. Notice that alpha plus or minus beta, alpha over beta, if beta is not zero, are all in A alpha beta, hence algebraic. Slick, right? You gotta love that. Don't know their polynomials, but I know they exist. So here is another corollary to the corollary. I pulled this out of this one separately, so I'm not gonna number this one. Let details. And one big notation here. I'm going to say K bar F is the set of alpha and F such that alpha is algebraic over K. Let me point out, just so I've got all my ducks in a row here, that if alpha is in K, then alpha is algebraic. So in particular, K bar F contains K. Otherwise, this would be a really stupid definition, right? So, what you do is you round up all the elements that happen to be algebraic. K bar F is a subfield of F containing K. Right. So we have K inside K bar F inside of F. Now, why is this a subfield? Well, precisely because of this here. Because if you have two algebraic elements, it's closed under addition, negative signs, it's closed under multiplication. So it's, and actually it's closed under division as well, as long as they're not divided by zero, so it's a subfield. And what can you say about the nature of these extensions? This and this.
The first one is finite.
Not necessarily.
Oh, no, necessarily.
Right, so for example, you could have your bottom field be Q and your top field be R. And if you look at the, all the algebraic elements, in R, they're algebraic over Q, basically, you get a lot of stuff, but it's only countable, right?
I think the last one is either trivial or non-algebraic.
Oh, very good, very good, very good. This extension is algebraic, that's an obvious statement. This one, and you're very careful with the details there, that's good. Either you have an equality in the last one, or this is transcendental, right? Because remember that theorem we have, if you have something in here that's algebraic over this, then because this is algebraic, if you have an element in here that's algebraic over here, it has to be algebraic over K, and so it would already be there. So either you have equality here, or this extension is transcendental. Okay, any questions? Okay, so we're gonna get going on the fundamental theorem of Galois theory next time. So this is probably, I've got an example that I think really does a lot to illustrate what goes on in the fundamental theorem of Galois theory. But let's start and kind of lay some of the road work here real quick. So let me give you some setup here. Let P and F be fields containing A, another field. We call a sigma from E to F a K homomorphism. Sigma from E to F is a K homomorphism, respectively, K odd morphism. if sigma is a field homomorphism, and a K vector space. Respectively, sigma from E to E is an automorphism. And a vector space. So what's the significance of this? Well, so basically this just means it's a ring homomorphism, all right? So sigma E1 plus E2 is sigma E1 plus sigma E2. Sigma of E1 times E2 is sigma E1 sigma E2, right? But it also means that sigma KE is K sigma E. So what does that mean about the effect? Right. So sigma must be fixed on K. It's the identity on K.
Why is it called the field homomorphism? I mean, is there anything else more than?
It has to be 1-to-1.
Okay.
Right, yeah, it has to be 1-to-1. Yeah, F is a field. And, the group of all K automorphisms. Group of all K automorphisms. Of F. And of course, it's a group because automorphisms are invertible, right? Is called the Galois group. F. And so this way, the K is important as well because you got to know what your base field Galois F over K. Sometimes do it this way. Sometimes rule lazy people like this way, because every G should be a Galois group. Right. So here's a final question. I'll leave this for you to think about. We resume discussion on Friday. Well, let's do this. Square root 2 Q. Think about those three. The Galois group of each respective extensions. What's the group of all of them?
The first one,
So, which one?
the first one, we have to map Q with Q, and then we can map the square root of 2 with the square root of 2, and a square root of 2 with minus square root of 2, right?
Well, so there's at least that, perhaps. So, yeah, think about these, see what you got. Any questions? All right, well, we will see you all on Friday.